Welcome back. We are here for demonstration number 2 for ECE 441. This lab is actually discussing pole placement and time response, or how do we, based on our original system, modify that with feedback. Recall what we had in the lab. You're going to remain with the system that you started with, the same spring, which I have not labeled, but let me go ahead and label that as K. You'll go ahead and put your spring back into the system that you started with, the same number of masses, and you'll need to remember what we had derived for lab number 1. And in particular, this describes the dynamical behavior of this mass spring damper system, which we can solve for the acceleration of the position x, and from this differential equation we can move over and determine or sketch a block diagram of that same differential equation in an all-integrator block diagram form. Here we have x double prime, and if you derive what this particular signal looks like, you should find the equation that we just had previous to that, and finding the closed loop or the open loop transfer function from the input u to the output x leaves us with k hardware over m over the denominator, and we see that we now have a pure two-pole system, no finite zeros, and 2 complex poles, probably, depending on your system. But for this combination of mass spring and dash pot, we should have everybody, all 16 systems, with the same, or I'm sorry, with similar complex poles, but they will be different or unique. They will be somewhat slightly damped relative to what we have a much smaller real part than we do imaginary part. The real part might be, in terms of magnitude, might be on the order of 1 or 2. The imaginary part is going to be somewhere between, let's say, 13 and 20. And so we have then minus, let's say, 1.5 plus and minus j 16 for the imaginary or for the complex roots associated with your mass spring damper system. What we're interested in doing, that's the open loop behavior. That gave rise to a given percent overshoot, settling time, and peak time. What we would like to do is actually modify that. And how are we going to modify that particular behavior? What we're going to do is what we were saying before, is we're going to try to change the dynamic behavior of the system by changing the pole locations, and we would like to do that without having to go in and change the spring, without having to adjust the dash pot, or without manipulating the hardware gain in the system. What we'll do then, in order to do that without physically changing the system, is we will do that electrically. By that I mean we're going to measure the position and velocity in our system from the mass as it's moving. We'll scale those measured signals, meaning we'll amplify those or attenuate those by some gain value. We have some position, velocity. The position we will scale by 0.1, for example, and then add that to a scaled velocity signal and feed that back into the input to modify our system behavior. We just said that we wanted to change the system behavior by measuring position, measuring velocity, and feeding those back into the input u to change the dynamic behavior. Let's just illustrate that on this board. This is what we started with. This is actually our physical system right here that we have in the lab. Let me say this is our physical system. We can inject the input signal and we can measure position, and we will also assume that we can measure velocity. We'll then change the open loop dynamics in this block diagram. We will still have the input u in the same location of our system, but now what I want to do is I want to actually measure velocity and scale that by, we'll call it a k sub 2, and feed that back. We will also measure position, scale that by k sub 1, and feed that back. And finally, we're going to have some reference input, which we will scale by k sub pf and put that in. And now we're interested in the dynamic behavior between the reference input, which is, let's say, 2,000 counts, and the position of that mass by what? In this new system that has now been changed into a closed loop set of dynamics, because we are now feeding back position and velocity, and we're also adjusting the reference input gain to the system. What we would like to do then is be able to change from this open loop behavior. Can we now move this pole from here maybe somewhere over to this location? And this new location will give us what? Much more damping and maybe even a larger natural frequency, which will allow us then to have a faster response. And what I want to do now is examine what this particular block diagram in the closed loop translates into in terms of governing differential equations. If we look at this particular system, we now have our x double prime equaling 1 over m times minus b x prime minus kx plus k hardware u. That's what we started with. That was the open loop system. What we now have done is we've now said, well, our input u is actually a combination of 3 different signals. It's now going to be some combination of velocity scaled, position scaled, and reference input scaled. What we want to do is see how that now impacts our closed loop behavior, meaning u of t is now minus k1x minus k sub 2 x prime plus k sub pf times the reference signal. Let's now put this particular expression for our input into our dynamic set of equations and see how that now influences the behavior. We now have x double prime is equal to minus b over m x prime minus k over m x plus k hardware over m all times minus k1x minus k2x prime plus k sub pf, let me just say r of t. What I would like to do now is perform these multiplications and actually combine like terms, meaning terms involving position, terms involving velocity, and I will only have one term involving our reference input. X double prime is now minus b over m, that's from here, but it's also minus k hardware k sub 2 over m, and all of that is going to multiply the velocity. We also have, maybe I should factor out the negative sign, it might be a little cleaner. Let me say that this is minus in that sense. Then I have minus k over m from the position, original position, plus, because I've now accounted for my negative sign here, k hardware k1 over m x plus K hardware K sub PF over M times R of T. This is now in the time domain our governing set of dynamics in the closed loop setting. That's our closed loop set of dynamics. We should now be able to find the closed loop transfer function from this, similarly to how we had found the open loop transfer function. All we really have to realize is that this is, in terms of what you're used to seeing possibly, this is now some minus B bar over M x prime minus K bar over M x plus some K, let's say, hat R of T. And if you feel comfortable finding the transfer function between R of T and X double prime, we should be able to find the transfer function closed loop for this particular differential equation and give us our closed loop transfer function T sub S, or T sub C of S. We're now moved over to another board, but we're just continuing our discussion on how does that feedback of velocity information and position information, how does that now change our system? We're now doing that electrically. We're not doing it with physically changing the damping or the spring. We're not going in and replacing the spring. We're actually changing the behavior of our system, changing or modifying the spring constant by measuring position and scaling that by K1, and that now, with the help of K hardware, allows us to modify our spring constant. We can also modify the damping, which influences our settling time in the system, by what? Measuring velocity, scaling that by K sub 2, and feeding that back to change B bar. Accounting for those modifications, or using position and velocity feedback with a feed-forward gain or a reference gain constant change, we can now derive the closed loop transfer function from the earlier differential equation in the closed loop setting. And we end up with this transfer function, which is our closed loop transfer function. This accounts now for position feedback, velocity feedback, and reference input gain constant modification. And we will now use this to allow us to modify our original closed loop pole location S sub 0 to a new closed loop pole location S sub C. We're now back to where we had almost started in terms of we have the closed loop transfer function. Let's relate that now to our standard denominators. Our denominator is a pure two-pole system, which we can represent as a real part of sigma and an imaginary part of omega sub d. This is now maybe where we would like our closed loop pole to be located. Remember, before it may have been up down here somewhere, for example. We can now try to, with position and velocity feedback, relocate that open loop pole to a closed loop pole corresponding to new values of zeta and omega sub n. And I'm just reminding ourselves what we have in terms of these standard denominators. We can either write it in terms of real part and imaginary part, or in terms of damping ratio zeta and natural frequency omega sub n. Either way, that tells us where this particular location is, or our desired dominant poles might be, based on sigma or damping ratio, or damped frequency omega sub d, or natural frequency omega sub n. We want to then, for all of these 16 different plants, we would like to have each of those start to look the same dynamically by using feedback. Suppose we want to have the following design specifications. We're going to impose 3 different specifications for this lab number 2. And lab number 2 is a little different than lab number 1 in that you need to actually do some pre-lab calculations before you go into the lab, and those pre-lab calculations depend on what you started with from lab number 1 and these new design specifications. For example, Suppose we now want a natural frequency omega sub n of 35 radians per second. That should be higher than what you had in the open loop system. Likewise, suppose that we want a percent overshoot of 10%. Not less than 10%, not more than 10%. Let's try to make it equal 10%. And the 10% overshoot should be different from everyone's open loop percent overshoot specification that they had. We also would like to have small or zero steady state error, which means that we would like our closed loop transfer function to have or possess a DC gain equal or near 1. If we can now achieve that, change our percent overshoot, and change our natural frequency, everybody, if they have a different system, will have a different position gain, velocity gain, and reference input gain to try to accomplish these three design specifications. We're now going to translate these design specifications into acceptable closed loop pole locations by means of trying to compare the standard denominator expressions to the closed loop transfer function's denominator expression, and that will then allow us to determine values for our position gain, velocity gain, and reference input gain. We were just discussing the standard design denominator expression, and now what we want to do is translate that or relate those design specifications of natural frequency and damping ratio to our physical system. And we can do that by comparing term by term this standard denominator expression with our physical system with position and velocity feedback introduced. If we do that for spec number 1, spec number 1 was concerned with changing the natural frequency of our system to 35 radians per second. That means we want to equate this to that. And in so doing, we see that the natural frequency squared, which we said for design spec 1 was going to be 35 squared, that's now equal to K plus K hardware K1 over M. The only unknown that we have, this is from lab number 1, that's your spring constant K. Omega sub n is a designed quantity. We want that to be 35 squared. M is however many masses plus the carriage you have. If we solve this expression for the only unknown K1, K1 will allow us to determine our scaling factor that we impose on the on the position signal that we measure. You will then calculate 35 squared times your mass minus the spring constant from lab number 1 divided by K hardware that you computed in lab number 1. That will give you your gain that you will use to adjust or modify the position signal that you're measuring. Specification number 2 similarly can be found by doing what? By looking at the linear coefficient in the standard denominator configuration and in the physical system. That now means that we can equate 2 zeta omega sub n equal to this B plus K hardware K sub 2 over M. This can now be solved for K sub 2. K sub 2 is now equal to, this is the gain on the velocity term, that's now 2 zeta omega sub n M minus B over K hardware. For design specification number 2, we've already said that we want zeta to correspond to what? 10% overshoot. And if you look in figure 5.8 of the text, a percent overshoot of 10% translates into a zeta value of 0.6. You'll plug that 0.6 in here. We said that we wanted a natural frequency of 35. That natural frequency will go in there. You know what the mass is, that's your given system mass. You've calculated the damping constant B from lab number 1. You introduce that variable here, and you've also calculated K hardware in lab number 1. Those quantities now taken in this particular manner will give us the gain that we need to use for our velocity term. Specification number 3, we will go to another board because that's going to be what? Working with the DC gain, and in that case, we're now interested in this particular ratio. What we want is a DC gain of 1, and that will now allow us to look at K is given, K1 we just determined, K is what we found in lab number 1, K hardware is what we found in lab number 1, M is going to actually cancel out. The only unknown that we have is K sub PF, and we'll determine that in specification number 3. Specification number 3 then says that we have the following, and maybe I won't go to another board, I'll just try to do it here. Specification number 3 says that we now have T sub C of 0 equaling 1. We would like to have our system track or follow the reference input command. That now needs to equal this K hardware, K sub PF over M, all over, and we'll find that by what? Setting S equal to 0 in this closed loop transfer function. K plus K hardware K1 all over M. From that expression, we can see that the masses can be eliminated. We can cross multiply, and we end up then with K plus K hardware K1 equaling K hardware K sub PF. K1 we just determined from specification number 1. K hardware is what we determined in lab 1, and K is the spring constant from lab number 1. We can now solve this for K sub PF by dividing both terms over here by K hardware, and we see that KPF is K1 plus the spring constant from lab 1 divided by the hardware gain from lab 1. This particular value for K sub PF is supposed to provide us with a DC gain of 1. Now, if there is an error in how we calculate or how we experimentally determined our spring constant K, or how we experimentally determined K hardware in lab 1, that's going to show up by having what? Some steady state error in the resulting expression. But here, if we had these experimentally determined very well, then this K sub PF value should get us close to a DC gain of 1 and allow our steady state error to be nearly 0. We're now into the lab, and what we want to do is, I'm going to assume that you can open up the ECP software by double-clicking on the desktop somewhere or finding it through the Start menu. You now have ECP up and running. You also should already have performed, before you come into the lab, the pre-lab calculations for lab number 2, which is a little different than lab number 1. You actually need to do some pre-lab calculations, actually steps A through J possibly. I don't know, those numbers or those steps may change, but essentially what you need to do prior to coming in is to calculate a position gain, a velocity gain, and a reference input gain value that you will use in the lab number 2 to generate new data. What you want to do then is, based on those assumptions being valid, you'll start the software, you will come up to utility and zero the position, because right now, before I do that, you can see that the encoder 1 position is not actually at 0, and we would like to start initially at 0. Let's go ahead and zero the position. We now have everything zeroed. We'll go over to the File drop-down window and Load Settings. We need to now come over to the C drive, the local disk C drive, go into the ECE 441 folder and highlight the ECE 441 _ lab2.cfg or configuration file and open that. Now that has loaded the software in with the appropriate values. We can now go to the setup and control algorithm. We'll click on the wrench box or the setup algorithm, assuming that the button is on state feedback, that has been highlighted and we are on continuous time. We'll click on setup feedback, and now case of PF, for this particular lab we can go ahead and re-execute under these conditions. If you have springs 1 or 2, you will be using 0.15. If you have springs 3 and 4, you'll be using 0.075. But for this particular demonstration, I have spring 1. I will go ahead and leave that as it is. I will implement the algorithm. I'll click on OK. I'll come back over and check the command. It should be step. I'll click on setup. It should do the step size of 2000 for a dwell time of 3 seconds, and repeat that under a closed loop step configuration. Remember, we do not have any feedback gains at this point. I will go ahead and execute that, and this is just to give us a sanity check to make sure that we have the same system that we had in lab number 1, that we're getting about the same response. And we can do this now to compare this to what we had in lab number 1, and also to compare it with what we are going to get for the controlled system in this particular lab. We will go ahead and wait for those samples to be loaded into the computer. We'll click on OK. We can go up to plotting, setup plot, and we're looking at the commanded position and encoder 1 position via the plot data, and this is what we have for the open loop system response, with the green indicating how our particular system evolves in time. We're now ready to go ahead and redo the lab with the gain values that we've calculated in the pre-lab calculation section of lab number 2. Again, let's zero out the encoder 1 position. We will now, in the setup, go to control algorithm, setup algorithm, and now we're ready to adjust our case of PF, K1 and K2 values. For my particular system that I have determined, I found that my KPF needs to be 0.5274. My K1, my position gain value, is 0.3762, and my velocity gain value is 0.017. I now can say that those are okay. All of these values are 0. I will implement that algorithm, click on OK. Everything is still 0. I'm in a closed loop mode, and I will now execute the same command that I had before, and I can watch and listen and see that I'm now tracking actually with just very few counts in error. I now have a 4-count error in my closed loop, or 3 count depending on the iteration. And that means that possibly those particular system parameters that I identified in lab number 1 are pretty accurate, and I will then examine the closed loop trajectory by clicking on plotting, setup plot, and plot data. And now you can see that I do have about a 10% overshoot. I'm trying to go to 2,000, and I overshoot that up to about 2,200, and then I lock on to almost a value of 2,000 counts. I have very little error, steady state error. I do have about a 10% overshoot, and I would then have to examine this data a little more closely. I could export this raw data by going to data and export and saving it to whatever file I would like to save it to. For me, it might be on my Z drive. For you, it might be somewhere on your Z drive. I won't do that now, but you should do that, and then you can analyze this data a little more carefully in MATLAB to allow you to get a better estimate based on the percent overshoot of your zeta value The rise time or the peak time will allow us to get an estimate on omega sub d. Zeta and omega sub d can then be used to find omega sub n and compare that with 35 radians per second. And our steady state error we can use to adjust our K hardware value if we need to, if we're off a little bit in terms of our position error. Let me, before I stop here in the lab, suppose that you have actually not very accurately determined your lab number 1 gains, or your parameter values for your spring constant K, your velocity or your damping coefficient B, or your hardware gain, and you have now started to implement a slightly different set of gain combinations, and you click OK, you implement the algorithm, and you're ready to then execute, and you hit run. And what I'm going to do, I hope, is this is going to actually throw the system into an undesirable state. I want to show you how you can get out of that condition. There are several ways. After I click on run, I'm going to hear the system complain because the values that I input are incorrect. And so if you input incorrect values and the system begins to complain, I want you to stop it either by pushing the red off button on the ECP control hardware box, or by hitting one of the stop buttons over here on the screen. And so I want you to be ready and able to do any or all 3 of those to stop the incorrect condition on the hardware. And what I did to stop it there was I actually pushed the cancel button. You could hear that I was vibrating or allowing the system to behave in an undesired condition. I'm going to go ahead and 0 the position and repeat that one more time and show that you can actually stop it multiple ways. The second time I actually reached over and pushed the off button on the ECP hardware box. It's now uploaded those samples, and if you wanted to, you could sort of look at what it was trying to do as it tries to execute that ill-conceived control strategy that I put in on purpose, but you may actually do it on accident, and I want you to know how to stop that either by hitting the cancel button here or by hitting the red off button on the ECP hardware. Hopefully you've acquired acceptable data and you're now ready to do some post-lab calculations with your lab number 2 data. We've now collected data from the lab, and what we want to do is analyze that data or do some post-data analysis on our collected data that we've taken in the lab. What we have is a compensated system. We've closed the loop based on 3 specifications. A specification number 1, which concerned, I don't even remember now, that was the natural frequency specification, omega sub n. Specification number 2 was our damping specification, or the percent overshoot or settling time, and specification number 3 was concerning our steady state error. Now, what we're going to do is we're going to redetermine those values, zeta, omega sub n, and omega sub d, based on our measured closed loop system response, and we'll compare that with what we thought they should have been based on what we had determined or said they should be in the pre-lab calculations. We have a pre-lab calculation that we've just found and used in the lab with K1, K2, and K sub PF. Now we've measured this kind of a response in the lab. We want to use this information to determine our percent overshoot, peak time, and steady state value. We'll first use the percent overshoot calculation by just taking the peak, subtracting from that the steady state value, and I've already made a mistake here. This should be then, so you won't make that mistake, over x steady state times 100, and that should give you now your percent overshoot. That percent overshoot can then be used in the formula to find the zeta value. This zeta value then that you've now calculated with your post-lab data should be, if you had identified your system properly from lab number 1 and had an accurate spring constant and hardware gain, this zeta should be very close to a zeta value of 0.6, which corresponds to a 10% overshoot. If it's not, if zeta is quite a ways away, let's say 15% off from 0.6, then what we want to do in the post-lab analysis is recalculate our system parameters based on the second data or the second lab's data collection information. But we've now, from our percent overshoot, from this peak, peak 1, and X steady state, we now have the ability to calculate our percent overshoot. From that we will calculate zeta. Again, that should be close to the 0.6 that we said it should be in this lab. We'll now go and look at that measured response, step response data, and calculate, or identify the time that it takes that system to peak. From the peak time, we will now determine a damped frequency omega sub d. The damped frequency omega sub d will now allow us to what? In combination with the damping ratio and the damped frequency, knowing what we know about zeta and theta, cosine of theta is zeta. We've found zeta from our earlier percent overshoot calculation. We can now find theta, and we know omega sub d from our peak time. We can use that to determine omega sub n, or we can say that omega sub n is omega sub d over the square root of 1 minus zeta squared, using this particular relationship and solving this for omega sub d. Solving this for omega sub n. That will then allow us to calculate omega sub n. This omega sub n should be close to 35. If it's not, then we maybe have identified our system a little inaccurately in lab number 1, and again we'll do some post-lab analysis to try to redetermine corrected values for spring constant, damping constant, and K hardware. And we will base that on these newly determined omega sub n's and zeta values that we've calculated or found based on lab number 2 data. We're now trying to re-evaluate or recompute system parameter values if you found that what? Your damping ratio zeta was not very close to 0.6. Maybe it was 15% off, so it's now 0.5 or less, or 0.7 or greater. Then we may want to reevaluate what our spring constant might be, K, our damping coefficient B, and our hardware gain, K hardware, because maybe lab number 1 didn't compute those as accurately as we would have liked. So what we want to do now is look at recomputing or recalculating our system parameter values, and those will be the K, the B, and the K hardware. New values from lab number 2 data. What we will do though is we will go back and continue to use these known relationships, and one of those relationships deals with comparing the constant term in the denominator expressions. Here is from our standard denominator expression, our natural frequency squared is equal to, in the closed loop system, K plus K hardware K1 over M. We can solve this expression for omega sub n squared M, and we will use that relationship to actually eliminate this expression in one of the following developments or derivations. But this is one of the equations that we will use. We now will use later the measured value that we had for the natural frequency, omega sub n, in the lab 2 data. We will use the mass that we have assumed that we know, and we know what we put in for k sub 1. That was a fixed number, and we'll try to use that information to our benefit so that we can recompute or recalculate the spring constant k. We can also use the constant term, or the S1 coefficient in the denominator. The standard form says that that's 2 zeta omega sub n. We'll calculate zeta. We've calculated omega sub n. This we said was off by 15% or more. Maybe omega sub n is off by 10%, so that it's now, what, not close to 35 in the sense of maybe it's less than 32 or bigger than 38, something like that. We can now use those recalculated values that omega sub n and zeta are and use those to recompute a damping coefficient B. We'll also use the relationship that we know between the input command R, which is 2,000 counts, and where we end up, x steady state, based on our closed loop transfer function. We know this is what we have in the closed loop, and for the steady state value, we know that we have the steady state value of our position is going to be the DC gain of our closed loop transfer function times the amplitude of our reference input, which we've been denoting by A, and in our labs we're assigning A to be 2,000 counts. Solving this expression for T sub C at 0, or the DC gain, we see that we now can do that by dividing both sides by A, or 2,000. We now have x steady state over A is the DC gain of our transfer function, and that's K hardware KPF over K plus K hardware K1. This has a few unknowns in it. We have K and we have K hardware, which we're now trying to recompute based on lab 2 data. And it would be nice if we could get rid of one or the other so that we would only have to recompute one based on this relationship. And from above or to the left, remember what we had for K plus K hardware K1. This particular expression right here is actually omega sub n squared m. Omega sub n squared is what we've now remeasured. This is maybe 32 or 31. Let's now use that relationship to eliminate K effectively in this equation, so that we can now use whatever we've now recomputed for our natural frequency, either let's say 31 or maybe 40. We square that, we multiply it by m, we set that, and we also know K sub PF, and we can use that now to determine new parameter values or recomputed parameter values, meaning K hardware, K, and B, based on closed loop measured quantities in lab number 2. For example, I've tried to indicate what we're doing by circling with green what we are now using to recompute K hardware. A is what? A we know, that's 2,000. KPF is whatever we used in lab number 2. So lab number 2 data is K sub PF. A we applied as 2,000. M is what we said it is. That's based on the number of masses and the mass of the carriage. What we have now calculated or computed from lab number 2 step response information is our steady state value for the position of the mass, our natural frequency, and we'll square that. We can now use these quantities to recompute a K hardware value, and hopefully that will be closer to the actual K hardware. We'll now use that in the second recomputed formula to now use what? We can now use this expression to solve for the new spring constant K. K is now solving this equation for K. We've just recomputed a new K hardware. We know what K1 is from lab number 2. We've computed omega sub n squared from the step response data, and m we know from our masses. That allows us then, using this newly calculated K hardware in this formula, to come up with a new spring constant K. We also can do the same thing, or a similar thing, to recompute our B value. Our B value, and up in this expression, K1 is what we picked or had been using in the lab number 2 computations. That's our position gain value. Likewise, K sub 2 is the velocity gain value. We can use a recomputed zeta, which is now less than 0.5 or greater than 0.7. Omega sub n, let's say, is less than 32 or bigger than 38. M is what we know it to be. Now we're using this relationship to recompute a new parameter value of our system, which will hopefully be a better or closer representation of physically what we have. Because now we have what? K2 is known, or we put that into the system. K hardware we've recomputed. Zeta and omega sub n are now the closed loop quantities that we used or found from the lab 2 data that we've just measured in the lab. And now we have a corrected value of B, K, and K hardware based on trying to locate our closed loop poles at a natural frequency of 35 radians per second and a percent overshoot specification of 10%, or a damping ratio of zeta equal to 0.6. Hopefully you've now been able to fine-tune your parameter values or not modify them at all if your closed loop behavior did provide a percent overshoot very close to 10% or a natural frequency close to 35 radians per second. And we'll have to pick up at this point. Now we have what? Lab 2 was using full state feedback to manipulate the closed loop poles of our system to give us a more acceptable system behavior. In lab number 3, we will modify that strategy and say we only have position information to feed back. Here we've used position information and velocity information, and we've allowed for adjustment of the input reference gain coefficient to be modified to allow our dynamics of the mass spring damper system to be modified to an expression or into a condition that we are more comfortable with.